A real-time clock, or RTC, is a device that accurately tracks the passage of time, a staple for timekeeping projects or projects that need to do some kind of scheduling. The PiicoDev RTC loses less than a second per year and features supercapacitor backup. That means that it can tolerate power outages of about a week. When connected to power, the supercapacitor charges, and if power is removed, that supercapacitor will keep the clock running so that it doesn't lose the time. I'm going to show you how to connect your PiicoDev real-time clock to a microbit. We'll get the correct time set on the real-time clock and observe how it can keep time even when power is removed. And then we'll experiment with some more advanced features like setting alarms and schedules. Let's get started. To follow along, you'll need a microbit V2, a PiicoDev real-time clock and adapter for microbit, and a PiicoDev cable to connect everything together. Plug your microbit into the adapter, making sure the buttons are facing up. Connect the cable to the adapter and connect the other end to your real-time clock. And I've just mounted everything to a PiicoDev platform to keep it nice and stable, and connect to your computer via USB. We're going to program in Thonny for this tutorial. If you need help getting started, there's a guide above, and if you prefer, you can use python.microbit.org if you prefer to use a web-based editor. Before we get programming, we need to download some drivers for the real-time clock. Find the download section in the article and select the correct dev board. Right-click PiicoDev Unified and save link as, and I'll save that to a PiicoDev folder in my documents. And do the same for the next link. I've got Thonny open and I've navigated to where I saved those files, and I'll connect to my microbit. Select the first file, hold down Shift and select the second, then right-click and upload to microbit. And there they are on my microbit. Jump back to the article and we'll get the first example. Find the set and read time and date example and copy all of the code from that example. Copy that and paste it into Thonny. This example has two parts. The first half will set the time and date that we select, and then the second half will display that time and date in the shell. Let's give it a look. We start by importing the device driver, and we also import a sleep function so that we can create a delay. Next, we initialize the real-time clock and call that RTC. So anytime we see RTC, we're referring to the real-time clock. Next, we have these properties, which will allow us to set the time and date. At the time of filming, it's the 18th of May, 2022, and it's 4:14 in the afternoon. So I'll set the day to 18. The month is fine, the year is fine, the hour is 4 in the afternoon, which is 16 in 24-hour time, and the minute is 14, probably coming up on 15. There it is. I'll leave the format in 24-hour time. You could use AM or PM if you wish. And now for the weekday number. Today is a Wednesday, which is the third day in the week, and if we count from 0, assuming 0 is Monday, that means that this would be a 2. I'm going to click the Run Current Script button, which will prompt me to save it to my microbit, and I'll just save it as main.py. And there we have it. In the shell, we have the time scrolling up. Let's just stop the script and take a closer look. So we have a couple of lines. The first line says the time is 16:15, which is 4:15 p.m., and then a line saying today is Wednesday. And then we just have these timestamps being printed. It looks like once every second. This is a standard format of year, month, day, and then hour, minute, and seconds. After we set these date time properties, we call the set date time method. This takes all of these properties and commits them onto the clock. So now the clock is running with this date time as a starting point. We can use the get date time, which does the opposite. It takes the current date time on the clock and loads it into these properties so that we can access them. So we call get date time, and then we do our print statements. The first line says the time is 16:15, and that is this first print statement here where we have the time is, and then we just convert rtc.hour into a string, and we concatenate that with rtc.minute. So we can access those properties individually if we want to, and we could do the same with the date or the weekday. In the next line, we're printing today is, and then we're using a new property called weekday name. That is the text name for the current weekday, assuming that 0 is Monday. So that's a neat way to extract the weekday name without having to do a bunch of other logic. So it's worth noting, anytime we want to access the current time, we have to call this getDateTime function. This is what queries the clock for the current date and time. If we didn't call that, then when we print the time, we would probably be seeing some old values. Next up, we have the infinite loop, and that's calling a new method called timestamp. Timestamp is a special function that automatically calls getDateTime and formats the result in this formatted date time string with year, month, day, hours, minutes, seconds. So that can be really useful for, say, writing to a data logger or creating some nice graphs. Now, the PiicoDev RTC does have power backup that should be able to keep accurate time during a power cycle. This is useful for battery projects that may only be powered periodically. Let's take that for a test drive. Head back to the article and we'll copy the next example. Here we have the running on backup power section, and I'll copy that example into Thonny. I'll just replace everything in main and save that. This is basically a stripped down version of the previous example. We're just printing the timestamp here. We don't want to run the previous script again, because if we did, it would reset the time back to those parameters that we programmed in. Now the clock has the time and we just want it to run. So if I run this script with Control R, we can see the time is still accurate. It's 16:20 and counting. And now if I unplug my microbit, I'll wait a couple of seconds and then plug it back in. I'll connect and reboot with Control D. And you can see we still have the accurate date and time. If the supercapacitor were completely flat, then we would be seeing the default date and time, which would read the 1st of January 2000. If you started with a completely flat supercapacitor, you would need to be powered for at least a few minutes before you could reliably handle a power outage. Now for a more advanced example, it's possible to program an alarm onto the RTC. This could be used for like a simple alarm that gets you out of bed in the morning, all the way up to more complex scheduling, where you could schedule an action to occur, say, on the first day of the month every month. Head to the advanced examples section and take a look at alarms and scheduling. We'll copy this example and paste it into Thonny. I'll just paste over everything in main. And this should look pretty similar at the start. We have the same imports and the same initialization. We're assuming that we already have accurate time running on the clock. And then the next action is to call alarm setup. And this is where we program when we want the alarm to trigger. In this case, we're passing in the parameter minutes equals 0. So that would mean to trigger once per hour at the start of every hour. Now I can see that we're currently 4:25 and 13 seconds. So I'll set this to the next minute, which is 26. I'll run that script. And now we're waiting for the alarm event. Let's take a look at the rest of the code. After we call the setup for the alarm to trigger on the 26th minute, there's an infinite loop. And all we're doing here is printing the timestamp as usual, and then calling the check alarm function. This checks whether we've crossed the next alarm time. If we do cross the time, we'll print the message alarm triggered, and then we'll carry on with the rest of the script. And we've just crossed the minute into 26, and you can see we have the alarm triggered condition. Now it's worth noting that the alarm will only trigger once. You can see here the alarm triggered the first time that the alarm condition was met, and that condition was for minute number 26, and that's when our alarm triggers. The minute is still 26 a couple of seconds later, but it's only that first time we cross the alarm condition that we get a trigger. This is really useful because it means we can keep checking the alarm, but we're not going to run the same action for every time we check it within that minute. Now you can get much more sophisticated with this. If we comment out that alarm setup and uncomment the next one, we can see we're passing in weekday 2, hours 13, and minutes 23. So what this means is, trigger on the third day of the week, say Wednesday, we're counting from 0, remember, trigger every Wednesday at 23 minutes past 1 in the afternoon. This is in 24-hour time. So this is a once per week action that will trigger on Wednesday at 1:23 in the afternoon. And we can also use date as a parameter. So we can pass in date 1, and this will trigger on the first day of the month. And if we're checking alarm quite frequently, it'll probably happen pretty close to midnight. So there you have the PiicoDev Real Time Clock being used for some basic timekeeping, keeping time during a power outage, and even for some pretty advanced scheduling so we can schedule actions to happen at some point in the future. And don't forget, there are plenty of other advanced examples for if you really want to squeeze all the functionality out of your PiicoDev RTC. We'd love to see what you make with this starter project. Perhaps you make a timer controlled light or an alarm. If you have any questions at all, please do let us know on the forums. We're full-time makers and happy to help. Until next time, happy making.